Okay. All right, so we're starting off with question 80 today, which is a good one. It's the last one on the study guide, so it's a good one to start with. Okay, so question 80 is a U-sub question, and for this one, it wants you to be able to identify what the U should be. So we talked about in recitation the process for doing U-sub and how you need to identify a composition of functions where the inner function, some like multiple of its derivative appears in the integral or integrand somewhere. So here we have x over the square root of x squared plus 1. And so when you're looking at this, you can see a composition of functions. In the denominator, you have the square root of x squared plus 1, where the inner function would be x squared plus 1. And if you take the derivative of x squared plus 1, you just get 2x. And there indeed is a multiple of that somewhere in the integral, because in the numerator, we have an x. So that is a good starting point. So let's go from there. So I'm going to choose my u to be x squared plus 1. That's just because, like I said, I identified a composition of functions, and then the inner function of the composition is equal to u. So now I need to be able to sub something in also for dx. So we're going to go ahead and figure out what dx is based on what we have here. So we have du equals 2x dx. And then if I want to solve for dx, I get du over 2x is equal to dx. Okay, so there is like an extra step here because our integral does have bounds. It's a definite integral, so we need to go ahead and also make a substitution for bounds. So when working with u sub, when you have bounds, you want to make sure that you also change them out in a sense, because if you've made a change of variable in the integral, but you haven't done anything with the bounds, it's not going to give you the same answer that you like should get. So we have to figure out now how to, I guess, do like a substitution with our bounds. So our lower bound is the square root of 3. And in order to figure out what we should write in there instead of the square root of 3, we just go ahead and plug that into this little relation that we found here. So I'm going to get the square root of 3 squared plus 1, which is just equal to 3 plus 1, which is 4, which means that my new lower bound should be 4 instead of the square root of 3, which is a lot nicer to plug in anyways. So let's do the top one as well. So I have 2 rad 2 squared plus 1. Okay, well, 2 rad 2 squared is going to give me 8. And then 8 plus 1 is going to be 9. Okay, so now I have my new bounds all figured out. So let's actually make the substitution now using dx, what u is equal to, and then also my new bounds here. So this integral now becomes the integral from 4 to 9. And then making the substitution, I get x over the square root of u. And then we have to plug in what we found for dx, where dx is du over 2x. And something nice happens here, like I said, it usually should, is that your x will cancel out. So you should officially now have a integral that's only in terms of u and nothing in terms of x. And then I'm going to pull this 2 out right here, just in the form of a 1/2 in front. So this is equal to the integral from 4 to 9 of 1 over the square root of u, oops, sorry, du. Actually, I'm going to go back and rewrite this even different. Sorry. I'm going to change it from 1 over the square root of u to u to the negative 1/2. Okay, so now this is something that we know how to integrate, which is the whole point of U sub, is that you start with something that looks pretty complicated and you have no clue how to integrate, and then you end up getting somewhere that you can integrate. So this is equal to 1/2. And then the integral of u to the negative 1/2, add 1 to the exponent. So we get 1/2 as the new exponent, and then we divide by 1, which is the same as doing 2u to the 1/2. And we need to evaluate it from 4 to 9. Okay, so now let's go ahead and evaluate this. And like I mentioned before, with u sub, at the very end, if you have like a definite integral, so you actually have bounds to plug in, you don't have to make that substitution backwards. So if you remember, like when we did indefinite integrals, we would start with like something in terms of x, go to something in terms of u, and then at the very end, we'd make that substitution backwards almost, so that we ended with something in terms of x. But here, when we have a definite integral with bounds, we don't need to. We already like did a substitution with our bounds, so we're good to go and just plug them right in, instead of having to like sub back in like at the end to get it in terms of x. So the whole point of changing those bounds is so you don't have to do that anymore.
Kaylee, if we do substitute, do we get the same answer?
So if you substitute it back in, as long as you didn't change the bounds to begin with, you'll get the same answer. So if I left my bounds as square root of 3 and 2 rad 2, and you sub it back in at the end, you'll get the same answer. And that's how I was always taught to do U sub, is to like, you don't change the bounds, and at the end you plug back in like the x, and then you're fine. I'm not sure if that's like technically incorrect, but no one teaches it that way. But you do get the same answer. So, yeah.
Thank you.
Yeah, you're welcome. Okay, so let's do our subs, or let's evaluate now. So this becomes 2, and then u to the 1/2 is the same thing as the square root. So I'm just gonna write 2 times the square root of 9. And then minus 2 times the square root of 4. And this is equal to 1/2 2 times 3 minus 2 times 2, which is 1/2 6 minus 4, which is 1/2 times 2, which is just 1. So you should get the final answer of 1, and that was a great question from Marty, that like if you do sub back in like what you know x is, or what you know u is equal to, will you get the same thing? Yes, only if you did not change your bounds at the beginning. So, yeah, I would stick to doing it this way, mainly because this is how they teach it in the textbooks, and how I think everyone teaches it in lecture. I don't know where I learned that other method of doing it. I think in high school. But yeah, I would stick to doing it like this just to be safe. Okay, that was question 80, but oh, and I did mention this at the very beginning before a few more of you came in. If you have any questions along the way, I didn't make a Jamboard like I usually do. You can just throw them in the chat, and then I'll just get to them when I finish the question. You can either ask out loud or you could throw them in the chat. So whoever has a question next.
Can you do 53?
Yeah. Okay. Man, the study guide is long. Okay. 53. So, okay, so we have the integral of 8 times the cube root of x squared minus 8 over the cube root of x dx. Okay, this is just going to be a matter of rewriting what you're given so that you do know how to integrate it. So all you need to do is take what you're given and write these expressions with exponents instead of like a cube root. So let's just go ahead and do that. So this is equal to the integral so of 8. But the cube root is the same thing as raising something to the 1/3 power. And then you have something squared under the cube root. So this is the same thing as doing x to the 2/3. And then just oh yeah, not too bad on this one. So -8, and then you have x to the cube root in the denominator, which is the same as x to the 1/3. But let's bring that term up to the numerator. So if we bring something from the denominator up to the numerator, you just need to make sure that you make the exponent negative. So this becomes 8x to the negative 1/3 dx. So if you ever see something like this on final or something, and you've got like roots and things like that, I would say like you can usually just rewrite it and then you're able to integrate it. Even though it might look super complicated, yeah, something like this, you're able to just rewrite like the roots as exponents and then you're good to go. So let's actually integrate now. This is equal to, so remember the 8's in front, we just kind of leave them alone. So I'm just gonna write 8 and then let's integrate x to the 2/3. So to integrate x to the 2/3, we add 1 to the exponent and divide by the new exponent. So 1 plus 2/3 is gonna be 5/3. So I have x to the 5/3. And then I'm going to divide by this new exponent, but whenever your exponent is a fraction, dividing by it is the same thing as multiplying by the reciprocal. So dividing by 5/3 is the same as doing times 3/5. Just like a nice, easy way to do it. Now let's do the next term. So now x to the negative 1/3. If we add 1 to negative 1/3, we get 2/3. So this becomes x to the 2/3. And then we divide by that new exponent. So dividing by 2/3, same thing as multiplying by 3/2. And then don't forget your plus c. Okay, so now let's just make this look a little nicer here. So this is what, 24 over 5, x to the 5/3. This will be 24 over 2, so just 12. 12x to the 2/3 plus c. And you're done. Any
So for
questions?
this,
Oh.
the problem, I guess I was kind of confused. I guess it's I wasn't looking at it correctly, but with the 8's in front, I kind of used that as like how I like integrated it, which made me get the wrong answer. So how do you know when to not really mess with the 8's? Is it because multiplied by the next
Yeah.
term or?
Yeah. So anytime you have like a coefficient, so if you have like 8x, that's the same thing as just pulling the 8 out. So like, okay, let me actually write this instead. So like the integral of 8x, like dx is the same as 8 times the integral of x dx. And that's as long as it's being multiplied, like you said. So as long as there's a constant like being multiplied by it, you're always free to either like pull that out of the integral or just like kind of leave it alone while you integrate. That's what I think of it as. But yeah, it's because it's being multiplied.
Okay, thank you.
Uh-huh.
And then for question number 45, like I got all the stuff to do it, but I just had a quick question on the graph.
Okay. Let me look at what the graph is.
Yeah, because if you just look at the answer key, I think that would help.
Yeah.
The reflection points that I got were I think there were 0 and 2, but whenever I graphed it, I didn't really know why they were that, if that makes sense, because there wasn't a change in sign on my graph.
Okay. Let me take a quick look at it. So the inflection points being at 0 and 2 are, so I think, are you graphing the actual, hold on, let me actually read the question. Okay. Okay. So the inflection points are where we talk about like changes in concavity. So actually, I'm just gonna share the answer key and talk about what the graph looks like. I think that would be a lot easier. Let me do- Okay. All right. So this is what the graph looks like on the answer key. Let's talk about it. So, okay. So yes, the inflection points are 0 and 2. And that's because the sign of the second derivative changes. And you can see that in the graph. So the inflection points, refer to concavity switching. So where your graph goes from like concave up to concave down, or concave down to concave up. So you can see that happens at 0 because right here, this is concave up, and then this is concave down. So you can see it goes from like being like, this is really weird to do with my hands, but like upward, and then it goes like downward almost, which is like the difference between concave up, concave down. And then same thing at 2, it switches back to being like concave up, I guess, in a sense. It's like the easiest way to say it. So yeah, I get that this is like a little trickier to see in the graph because it's not like a super, I mean, I feel like the one at 0 is like, you can kind of tell that one, but like the one at 2 is a little more subtle in my opinion. But yeah, it just goes into the fact that the function switches concavity at those points.
Okay, thank you.
Yeah. Okay. Let me go back to my OneNote. Okay. Let's see. Did we already do 53? I think we did. Yeah, okay. Any other questions on anything on here? Anything at all? There's 80 problems. Someone has to pick. Oh, good. There's a chat. 34. Okay, let's do 34. Oh my gosh. The document is way too long. Okay. 34. Everyone's like least favorite problems. Given a graph, sketch the other graph. Okay. Yeah, these ones tend to be okay, and then 40 after. Sweet. Okay. These ones are kind of tricky, I think. Just going from one graph to the next, it's never super easy, and really like I think just practice is like the best way to get better at it. But something I guess that I can say is if you ever are trying to go from the graph of the function to the graph of the derivative and you see a straight line, that is a very good indicator that you are going to just find the slope of that line, and that's your derivative. So if you see anything like this, it's just a straight line, you know how to find the slope of that, just by like rise over run from algebra. And the slope of that line is the derivative of that, of if that, oh, wow, words, at all those x values. So if you ever see a straight line, find the slope of it, and that is going to be the derivative at all those x values. So let's just do that part first. So just rise over run from algebra. So rise 2, run to the left 1, so that would give you a slope of -2. Because I rose 2 and went to the left 1, so this is -2 here. So I know that from my x value of -2 on to -infinity, my derivative is going to be -2. So if I come down here, and remember that we use the little open circles here because this is it's a sharp turn, which means that the derivative should be undefined at that point. So you don't want to do like a shaded in circle here. Okay. Let's do the next one. So I rise 2, go over 1. So this one has a slope of 2, which means that from x values of 2 all the way to infinity, my derivative is going to be 2. Okay. Now we just have to tackle this like inner piece here. So something that will help you graph the derivative is noticing that right here, the slope of the tangent line would be 0, which means that at 0, the derivative should cross the x-axis. Okay. So at 0, your derivative should cross the x-axis because the derivative will be 0 there, because the slope of the tangent line is 0. Hopefully that makes sense. So we know that here our derivative crosses. So let's see. from -2 to 0, my function is increasing, which means that my derivative will be positive. So we're going to have a positive derivative. And then let me use a new color. Then from 0 to 2, our function is decreasing, which means our derivative will be negative. So we know that from -2 to 0, it's going to be above the x-axis, and from 0 to 2, it will be below the x-axis. So this gives you an idea of what it should look like. And that's simply because the derivative is undefined at 2 and -2, and what we've drawn right here demonstrates that. You've got a function that goes right along, -2, but it doesn't have an output at -2. Same with 2. So just dissecting the pieces of the graph, that's a good option for the graph of the derivative. Let's see, let's do question 40. Okay, question 40. Oh yeah, I think I know. Well, yeah. Okay, so there were a few of these questions like this on the recitation worksheets, where it gave you like I don't want to say complicated, but I guess kind of like a confusing limit or something that you don't really know how to solve. Um, and you're supposed to use the fact that like the limit definition of the derivative. So like the limit as x approaches a of f of x minus f of a over x minus a is just f prime of a. So you're given kind of a complicated looking limit, and you're supposed to use the fact that this is ultimately just the derivative evaluated at some value. So let's write down what the limit definition of the derivative is. So we have f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. So by comparing these two, or by comparing this with what we're given, you can see that there's some similarities here. So in our case, we've got the limit as x approaches e, and in the denominator, we have x minus e. Okay, well, that matches up exactly with the definition of the derivative. And then in the numerator, we should have f of x minus f of a. Okay, well, if f of x is ln of x, ideally, we should have minus ln of e, and ln of e is 1. So sure enough, we do have this limit that exactly matches the limit definition of the derivative. So this is really just equal to f prime of a, where, where f of x is equal to ln of x. And a is e. There we go. Okay, so this is really what we're given here. So all you need to do is actually find the derivative of ln of x and then substitute in e. So f prime of x is going to be equal to the derivative of ln of x, which is just 1 over x. And then we just need to find f prime at e. So f prime at e is just equal to 1 over e. So yes, these are kind of tricky because I don't know, if you have a hard time recognizing that it looks just like the limit definition of the derivative, yeah, I can see why this would be really difficult. So maybe just that's something to keep in mind, that if you're doing a limit on the final or something and you're not quite sure, maybe that's something just to check for, is be like, oh, hey, does this match up with the limit definition of the derivative? And if it does, yay. So just like keep that in mind, that is a way that you can technically solve complicated limits, because it's not one that's like, I guess, thought of commonly. Okay, any questions on this one? Okay. Okay, question 50. Okay, good old differentials. Okay. So use differentials to approximate the change in the volume of the cube. Okay, when the length of the side changes from 5 to 4.97. Okay, well, you do have to have an idea of what like the differentials, like, I guess, like property of approximating is. So first, let's just go ahead and write our, I guess, like a function out for the volume of the cube, because our question is about the change in the volume of the cube. So you're probably going to need the equation for the volume of the cube. So this is v of x is equal to x cubed. Okay, so that's the volume of the cube. And then the question wants us to use differentials to approximate the change when the length of the side changes from 5 to 4.97. All right, well, differentials says that, I'm trying to think of like an easy way to say this, essentially that with the equation we have, that dy is equal to v prime of x dx. So without like mathematically being incorrect, like you usually have dy dx is equal to v prime of x. Although this is definitely like not the like mathematically correct way to explain this. Differentials basically says that dy is actually equal to v prime of x dx, which is very similar to this. But this is what differentials tells you. So let's go ahead and use that. So dy equals v prime of x dx. Okay, well, let's plug in what we have. So v of x in our case is x cubed. So v prime of x would be 3x squared. So we have dy equals 3x squared dx. Okay, and then we do have other things that we know about this. So we know what x is, and we know what dx is as well. So let's go ahead and write those down. So our x in this case is going to be the length of the side. So it's going to be 5. Oops, sorry. Okay, it's 5 because our side changed from 5 to 4.97. So we start with the side length of 5. And then we also have to write down dx, which is going to be the change in the side length. So we go from 5 to 4.97. So it decreases by 0.03. So your change is negative 0.03. If it went from 4.97 to 5, your dx would just be 0.03. But it's negative because it's decreasing. Let's plug these in now. And just plugging these in will give us an approximate answer. So dy is equal to 3 times 5 squared times negative 0.03. Okay, well, let's see. 3 times 25 times negative 0.03 is going to give us negative 2.25. Okay, and it should just be, what, let's see, centimeters cubed, yeah. Okay, yeah, so differentials is just a way to approximate the change in something, using the fact that, dy dx is equal to the derivative. Okay, so then maybe we can say dy is equal to v prime of x dx. So that's ultimately where that concept comes from, and then we just plug in what we know. Okay, that was question 50. Anyone have any other questions they want to throw in? Oh, there's another one, question 10. Okay, let's do that one. If you think of ones while I'm going, just send them in the chat. Feel free to. I'll get to them. Okay, almost there. Yes, the limits section. It feels like that was so long ago. Okay. All right, let's see. Okay. So the limit as x approaches 0 from the right of x squared ln of x. Okay, so let's actually like plug this in and see what we get. So if we do plug in 0, we get x squared, is 0 squared. And then ln of 0, negative infinity. Okay, so we get 0 times negative infinity. So this, I guess, is maybe a good indicator that you should try using L'Hopital's rule here. So let's maybe see why. So let's rewrite this because we can. So we have ln of x times x squared. We can definitely rewrite this as something that L'Hopital's rule can apply to. And I know we did like one of these similar in recitation, but I think we only ever did one of them. So you can definitely rewrite this as ln of x divided by 1 over x squared. And so now, if you go ahead and plug in 0, you'll get infinity over infinity, which is a good indicator that we can use L'Hopital's rule, since that's an indeterminate form. So 0 over 0, infinity over infinity, you are good to use L'Hopital's rule. Okay. So let's go ahead and apply this. So L'Hopital's rule says we need to take the derivative of the numerator over the derivative of the denominator. So this becomes the limit as x approaches 0 from the right. And if we take the derivative of ln of x, we get 1 over x. And then if we take the derivative of 1 over x squared, that's the same as x to the negative 2. So this derivative is negative 2 x to the negative 3. Okay. Let's see. Hold on. Give me 1 second. I'm looking. Okay. I'm going to do this a different way for simplifying it. So this is equal to the limit as x approaches 0 from the right of 1 over x divided by negative 2 over x cubed. Yeah, okay. And when you have a fraction divided by a fraction, that's the same as the numerator multiplied by the reciprocal of the denominator. So this is equal to the limit as x approaches 0 from the right of 1 over x times x cubed over negative 2. And so that's equal to x squared over negative 2. Okay, and then if we go ahead and plug in 0 here, we just get 0 over negative 2. So it's literally just 0. All of that just to get an answer of 0. Just a L'Hopital's rule problem with a decent amount of manipulation involved. Okay, and then we have a question on number 11 as well, so let's keep it coming. Okay, so this is, okay, the next one coming up is L'Hopital's, but like with, I think you use ln and like that rule. Okay, yeah. So this is, okay, this is the limit where x approaches 0, 1 plus 2x, 1 over 3x. So we have to use that rule that we talked about a really long time ago, it feels like, in recitation, where you do some manipulating with e and ln so that you're able to rewrite it in a way that you can actually evaluate. So let me move my work really quick. That way I have room. Okay. So we rewrite this as the limit as x approaches 0 from the right. And then that little like rule or like procedure that we learned said that you do e to the 1 over 3x times ln of 1 plus 2x. And I remember like briefly explaining this in recitation, but the reason why this works is because if you were to simplify this out, so if you went ahead and simplified this expression, you get exactly what you started with, but just rewriting it in a different way allows us to just look at the exponent and then actually evaluate the limit. So the cool thing is that because we've written this as e of 1 over 3x times, okay, that whole thing, we can actually just look at the limit of the exponent, and then we can kind of bring the e back in at the end. So that's the best way that I can describe it, is that you can look at the limit of the exponent and then bring the e back in. Okay, so let's only look, well, this is what we're working with, but let's just look at the limit as x approaches 0 from the right, only of 1 over 3x, or let me write this as ln of 1 plus 2x over 3x. There we go. Okay, so this is now something that, let's see, can we just plug right in? Okay, so if we plug this right in, we will get something that's in indeterminate form. So we're going to need to go ahead and use L'Hopital's rule here. So good old L'Hopital's rule. So this becomes the limit as x approaches 0 from the right. And then to take the derivative of ln of 1 plus 2x, that's going to require a chain rule. So the derivative of ln of x is 1 over x. So in this case, we have 1 over 1 plus 2x. And then you need to multiply it by the derivative of 1 plus 2x, which is just 2. Derivative of the denominator is just 3. And now let's actually try to plug in 0 and see what happens. So if we plug in 0, we get 1 over 1 times 2 over 3, which is just going to give you 2/3. Don't stop here though, because remember at the beginning, we went ahead and just disregarded the e in a sense, and we looked at the exponent. So now we have to bring the e back in, and your answer becomes e to the 2/3. Okay. All right, so we've done 10 and 11. Who else has a question? $74. Okay. Let me scroll down to 74. Okay. All right, so find the average value of the function f of x equals 25 minus x squared on the interval 0 to 4. Okay, so average value is kind of just like integration with an extra step in it almost. So average value of a function on the closed interval, let me just write it out actually. So the average value of f is equal to 1 over b minus a times the integral from a to b of f of x dx. And so the interval you're given is a to b. So in our case, we were given 0 to 4. So like our a is 0 and our b is 4. Okay, so all we need to do is kind of plug in what we have into this formula here. So if you're given a function on a closed interval and it wants the average value, you're going to integrate across that interval and then just divide by, or sorry, multiply by 1 over b minus a. And b minus a is just the like length of the interval. So kind of makes sense when you think of like the average value, because you integrate it and then you basically divide by the length of the interval. So, okay, let's plug in what we're given here. So we have 1 over, and our b is 4 and our a is 0. So 4 minus 0, so this is just 1/4. And then we have the integral from 0 to 4 of 25 minus x squared dx. Okay. So now we need to actually integrate this. So this is equal to 1/4 times, and to integrate 25, it becomes 25x. Integrate x squared, you add 1 to the exponent, so it becomes x cubed, and then you divide by 3. So minus x cubed over 3. And then we just need to go ahead and evaluate it from 0 to 4. Okay, so let's plug in these bounds here. So first, we go ahead and plug 4 in. So we get 25 times 4 is going to give me 100. Minus 4 cubed over 3. So what, 64 over 3? Yeah. Yeah. Okay. If we plug well, sorry, we'll subtract and plug in 0 here, but if we plug in 0, you get 0 because you get 25 times 0 minus 0. So this is just like subtracting 0, but just for the sake of writing it. So this is equal to 1/4 times 100 minus 64 over 3. So let's see. Okay, yeah, let's get a common denominator here. I think that's probably gonna be the simplest way. So 1/4, and then this becomes 300 over 3 minus 64 over 3, which is 1/4 times 236 over 3. And then this just becomes 236 over 12, which, well, let's see, you can divide that by maybe 4. Let's see. Yeah, so this becomes 59 over 3. So average value on a closed interval is just integrating across that interval and then basically dividing by the length of the interval or multiplying by 1 of them. Okay, good question though. All right, what's next, everyone? $79. All right. All right, we did 80. Now let's do 79. Okay. Let me move my work over. Oh, oh, my poor laptop is like overheating. Hold on. Oh my gosh. Okay. Whatever. I'm just gonna do the work over here. Okay. 79. The integral from 0 to ln of 4 of e to the x over 3 plus 2 e to the x dx. Kind of nice, and this problem tells you what to use for u. So that's kind of helpful in this situation. So let's just start by running with what they give us of what to use for u. So if u is equal to 3 plus 2e to the x, let's see, what would du be equal to? So du would be equal to, derivative of 3 is just 0. And then the derivative of 2e to the x is just 2e to the x. Okay, I'm gonna just. Okay, so then this means that du over 2e to the x is equal to dx. Okay, great. So like I said earlier, we are trying to do a like change of variables almost in our integral. So we're going from everything being in terms of x to everything being in terms of u. So now we know what to sub in for, 3 plus 2e to the x, and then we know that we need to plug in for dx du over 2e to the x. But the other thing that we need to take into account is to do a change of the bounds of the integral as well. So let's do that. So let's do our bounds really quick. Okay, so to change the bounds, we found that relation that u is equal to 3 plus 2e to the x. So all you're going to do is plug your bounds in for x here. So if, so let's do 0 first. So we get 3 plus 2e to the 0. Okay, well, e to the 0 is just 1, so we get 3 plus 2, which is 5. All right, cool. Let's do our next one. So we have ln of 4. Sorry. So let's plug ln of 4 in for x. So we get 3 plus 2e to the ln of 4. So remember that e and ln are reciprocal, no, inverses. Oh, sorry guys, it's early in the morning. So e to the ln, they work as inverses and they kind of like cancel each other out. So e to the ln 4 is just 4. So this is equal to 3 plus 2 times 4, which is just equal to 3 plus 8, which is 11. Okay, so let's take everything we have. So we have this relation, and then we've also got this thing for dx, and then we've got our bounds as well. So let's make that substitution. This is the integral now from 5 to 11 of e to the x over u times du over 2e to the x. Okay, so this is nice because like we mentioned, the e to the x's will cancel out, which is what you're looking for. So this cancels out, this cancels out. And you just end up getting the integral from 5 to 11 of 1/2 1 over u du. Okay, this is now transformed into a much simpler problem that you all know how to integrate. So this is equal to 1/2, and then the integral of 1 over u is ln of the absolute value of u. So this is ln of u, and we need to evaluate it at 5 to 11. Okay, and then remember what we talked about earlier, that because we already made a change of bounds at the very beginning, we don't have to go through that process of subbing back in what like u is equal to. So you don't have to go through the process of, oh, I have something in terms of u, now let's go back to in terms of x. We've already kind of done that by making the substitution on the bounds. So at this point, we're good to just straight up plug in what we have. So 1/2 times ln of 11, oh, God, it's weird. ln of, okay, sorry, we're just gonna do this. ln of 11 minus ln of 5, and that's it, you're done. Okay. Probably have time to do like 1 or 2 more questions, depending on what they are. So if anyone wants to go ahead and claim those next questions, feel free to send them in the chat. Or say them out loud, I don't care. $54, okay. Okay, so did 53, but let's do 54 now. So I believe this is just another case of like manipulating. So we have t plus 2 over t squared. So this is kind of similar to 53 in the way that you start with something that you don't know how to integrate, and then you're able to just do like some, I guess, like simplification or move some things around, and then you'll find something that you're able to integrate. So let's do that. This is kind of a like, I don't know if common's the right word, but we've seen problems like this before where you need to split it up over the denominator and then you're able to simplify a little further. So let's do that. So this is the integral of t over t squared plus 2 over t squared dt. Just an algebra reminder that you can split things up over the denominator, but you can never split things up over the numerator. So just a little algebraic reminder here. Okay. So now this is nice because we can simplify these two terms, and then we have the addition of things that we know how to integrate. So this is equal to t to the -1, or sorry, 1 over t. Better way to write this. 1 over t, and then this one would be 2t to the -2. Okay, so 1 over t is one of those like special integrals where we know that the integral of 1 over t is ln of t. So this is equal to ln of t. Oh, it should be the absolute value of t. ln of the absolute value of t. And then our next term is just one of the like power rules. So add 1 to the exponent and divide by that new exponent. So if we add 1 to -2, we get -1. And if we divide by -1, this just becomes minus a 2 over t. Yeah, 2 over t. And then do not forget the plus c. So whenever you're doing an indefinite integral, don't forget that plus c here. Very key. If you have bounds and you get a number as your answer, you do not need a plus c. Okay, we probably have time for one more question. So if not, though, we can totally stop. But if anyone has one last question, we can do it.
I kind of have a question on 54. So
Okay.
I just did my work wrong, but for like that second row, I got 2t to the -2 or -1 maybe for the I didn't know if I did that wrong or
So like, sorry, let me highlight this part.
yeah.
Okay. So let's see. So let's just go through why that simplified to be that.
Okay.
So t over t squared is going to give you 1 over t just by like some algebra rules that like one of the t in the numerator can cancel out with one of the t's in the denominator. So you're just left with 1 over t. And then for the second term, just 2 over t squared. So just to bring it up into the numerator, it just becomes 2t to the -2. And that's really it for the simplifying.
Okay. I just looked at it wrong. Thank you.
Okay. All right. Any last questions? Okay. I'm gonna stop sharing my screen. So stop recording.